Yeah. Go quickly. All right. This is the one that starts. The graphs start on 7, right? Am I looking at the right paper? That's the one y'all have. Okay. Which one did y'all say first? I'm sorry. 12. Number 12. Oh, it's a piecewise. Jogger. I'm just writing away. Thank you. All right, here we go. Number 12. Follow along on your homework. All right, let's do the first two. Should be fairly easy for you, right? That's the old what we've been doing. So f of x equals 1 is what kind of a graph? What's it look like? It's just a what? Horizontal line. So I start at -5 and I get 1, and then I'm going to continue on in that direction. Let's see. 1, 2, 3, 4, 5. Open or close at 1, -5? Oh, -5, 1. I'm just kidding. I'm dyslexic today. I wonder what could have happened. Very hard to concentrate with the distraction of you. -5, 1. Open. And then horizontal line going to the left because it's less than. Second piece here, I'm going to plug in -5. And when I plug in -5, what do I get? Y'all can do this. 5. So -5, 5 is going to be open or closed?
Close that thing up.
Then plug in 3, and what do you get? Open or closed?
Close it up.
And these just connect. Now for the last one, this is where it gets a little bit more complicated, but we're going to use the easy way that we talked about Friday. I'm going to plug in 3 first, and when I plug in 3, what do I get? Anybody? If you plug in 3, you get -6, right? So is that open or closed? Open. So 3, -6 be down here. Now, I need to check the vertex. What's the vertex of this absolute value? Come on, guys. 4, -7. Is that 4 bigger than 3? Yes. So it's in my area here, and I need to include it. So I'm going to do 4, -3. Remember, that's my vertex, so that's where it's flipping over.
Shake back.
All right. Cool. Just hold on for a second. 4, -7. Here we go. Sorry about that. So now the question is, this connects, right? And this is my vertex. Well, what happens at a vertex? Why is it important? What happens there? It flips over, right? It stops doing this and starts going up. So all I have to do now, because I already have this one point, I can just reflect it over. And there's what the rest of my graph looks like. How about the domain? How about the range? Why don't you stop here for the range? Because this line down here is continuing to go up forever, so it takes it up to infinity. What else? 13. Yeah. 14. This one's an inequality, so it tells me two things. Number one, it tells me if I am solid line on my graph or dashed. Which one is this? Dashed, because there's no line under it, and it also tells me which way to shade. In this case, that's right, I'm shading below. All right, so where is my vertex here? What am I missing in my equation? It's h, that's right. That number inside the absolute value, right? So here, since it's missing, I'm going to let it be 0 and then 6. So my vertex is 1, 2, 3, 4, 5, 6. Oh my God. Pick an x close to the vertex. What shall I pick? Or, oh, actually, we didn't do that. We did it by slope, didn't we? Sorry. If the slope is -2, that means I'm going to go down 2 and over 1, right? Reflect and connect. We said it's dashed. And shade down.
Did I get it right? Yes. Let's go.
Other questions?
So say we got like, I know how to do it now, but say we got like a fraction, right? Would the rise over 1 be 1, 4?
Yes. So up 1 over 4. Yep. Anything else? Going once. Number 9. F of x equals 1/3 absolute value of x minus 7. What is my vertex here? 0, -7, right? 1, 2, 3, 4, 5, 6, 7. Now the slope is 1/3, so I'm going to go up 1 and over 3. Reflect. Connect. I think we have run this in the ground. All right, going once. Any other questions? Twice? Yeah. Sold. All right, you need a pencil, and that is it. If you want your calculator, embrace. Just from now on, don't even call me Miss McGee. Just call me Elle McGee, and I'll answer. Yes. All right. Everywhere, Elle McGee. That's the only thing I'll answer to from now on. That's fine. I won't answer because I'm not a W. But I'll only answer when addressed Elle McGee. You're welcome. You've heard of parent functions before. What? There's a couple new things I need to show you in here. So I'm going to give you some parent functions, and this is going to be the basis of your project, is using these parent functions to do things, and we'll talk about all those things with which you also will have, your homework will come from an entire packet given to you that I will give you tomorrow for the remainder of this unit. So if you're like Noah, if you're like Logan who wants all your homework ahead of time so you can work ahead, you'll have, and it won't be due until like next week. It'll be in the entire packet, but it's thick, so don't let it intimidate you. So we'll have a packet and a project. So this is lots of opportunities for grades in this unit as we wrap up this 9 weeks, which is coming up soon, right?
That means report card?
That means report cards. Can you believe it?
Oh my God.
Hooray!
This school year was awesome. How many more weeks?
When does third quarter end? Third quarter ends
Not soon enough.
We say like, don't say March, just like April.
March 10th.
Oh! This was a lock in.
So you've got the rest of this week plus 1, 2, 3 more weeks.
Alright, no slip up from here on out.
How many steps do we have to do?
Yeah, halfway through.
How many more
we're
tests?
halfway there. What? Probably 2. Yeah, it's time to lock in. If you haven't been locked in before,
Don't worry.
lock in now.
I've been locked in since we had
I had like an 83 at one point.
You can't say that when at the very beginning when there was 2 grades.
No, I'm talking about like a week ago. I had like 83.
Yeah, then what happened? You fell asleep.
All right.
Then I got comfortable.
Never get comfortable in here. Parent functions. Before we talk about parent functions, I'm going to talk about some analysis that we're going to do with each parent function. Some of this analysis you've done before and you know, and some of it you haven't. So I'm going to digress just a minute. We've talked about domain and range. We will do domain and range for every parent function. I'm not going to go over that because we have been drilling domain and range. For domain is your X, range is your Y, left to right for domain. Yeah. From the bottom up for range. Okay. X-intercept. I'm going to go ahead and give you these so that you know why I'm going to. You just take one and pass it. Charlie Ray.
What did he say?
Email Mallory.
I said, take one of these and pass it. He said, what if I don't want to? And then he took one and passed it. All right. X-intercept. Tell me what that means. Crosses the x-axis. That's graphically. How about algebraically? What happens at an x-intercept? Uh-oh, y'all don't know this.
What? I didn't know what.
All right, let's think about this. Every time I cross the x-axis, no. What's 0? What, somebody said it. Not x, but y. Okay? Every time it crosses the x-axis, y is 0. If you don't believe me, put some points on the x-axis and name their points. This would be 1, 0. This point, 4, 0. In fact, anywhere that I go on the x-axis, that is true. Do we agree? Yeah. So algebraically, if I had an equation, I could put 0 in for y and solve it for x and find the x-intercepts. That's why sometimes we call x-intercepts solutions. Yes. Sometimes we call them roots. Sometimes we call them zeros. All of those describe the exact same thing, which is the x-intercept. Did you have a question, Logan?
Would it not make sense for the thing to start to the right to come together and like
Okay. Questions about x-intercepts?
Wouldn't that be cool?
Who the heck is gonna bring their baby to start teaching?
I'm sure in China it's talking to them. How are you not native speaking?
All right, same concept here. What's a y-intercept? Crosses the y-axis. Again, that is graphically. What algebraically happens at y-intercepts? X equals 0. You're exactly right. So again, if I have an equation and I need to find the y-intercept, I could just plug in a 0 for x, solve it for y, and I would have my y-intercept. Everybody good? Sure. All right. We'll save in behavior. I'm going to come back to it. And I'm going to do continuous or not. I'm going to give you a very basic definition of continuity. If you can draw the graph Have we not talked about this? Sometimes I start getting pre-cal blends in with you guys. If I can draw the graph without picking up my pencil, then it's continuous. Most graphs that we deal with are continuous, with the exception of a couple. The piecewise that you've been doing are not always continuous, right? Sometimes, if they look like this, can you draw that without lifting up your pencil? No, because I'd come here and I'd start going, boo, 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 boo. Oh, wait, I got to jump up here and finish the graph, right? So it's not continuous. So we would call it discontinuous. Yes. If I have a normal, let's just say a quadratic like we've been doing before, is that continuous or discontinuous? Continuous. I did not have to lift my pencil at all to draw. There are no holes or gaps in my graph. It is continuous. Does that make sense? Very basic definition. Yes, Mr. G, that makes sense. Good, I'm glad. Okay.
That makes sense.
In behavior is where this is going to be totally new to you. So buckle up. Strap. Is that what you just said? What are you saying? No. Which still doesn't matter to me because I still don't know who y'all are talking about. Okay, in behavior, how many ends? And we're gonna say for a normal graph, how many ends does it have? Two, right? And they do different things. So in behavior is going to describe both of those ends. So there will be two mathematical sentences to describe. And if you look on your sheet, you can see for every in behavior, it's partway filled out for you. But let me show you what's going on. I start out with as X, and then I have this little arrow. This little arrow means approaches. And then you have a blank. Then it says f of x approaches, and you have a blank. So let's think about this for a minute. I'm going to use infinities here, either positive infinity or negative infinity. And since I'm talking about two ends of a graph, I'm going to write this twice. Now, let's look at the x side first. And let's just do a general. Oh, I'm sorry. Let's just look at, okay, look at the first sentence. Let's just look at a quadratic first, for example, okay? I'm going to say that the left side of this graph is when x approaches negative infinity. Would that make sense to you? Okay, so let's think about it. If x approaches negative infinity, that means x is getting really, 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 really small, right? Which direction does x get smaller? The arrow. X is my horizontal axis, right? So this is 1, 2, 3, and so on. This would be -1, -2, -3. Which way, left or right, does x approach negative infinity? To the left. So anytime I see this, this means look at the left side of the graph. Does it make sense? Why? If I'm on a number line, this way is what? Positive infinity. This way would be, so if I said look towards negative infinity, which side are you looking? To the left. Okay? Are y'all with me now? It says as you look to the left, what is the graph doing? Look on at the left side of the graph. So for this one, here's the left side. What is the graph? Because f of x is y. What is y? What is my y value doing? The further you go left, what's happening to y? The bigger it's getting. Do you see that? As I keep going this way, if I kept going, it's getting higher and higher and higher, right? The further I walk this way, the higher that graph is getting. And it's what? I'm looking at the y. F of x means y. So as x moves to the left, y goes up. So this means up. Now there's two ends. That only describes the one end. Let's describe the other end. As x approaches this time positive infinity, so this time look to the right, what is the graph doing? It's going up again. That's all we're filling in. I'm just dipping your toes in end behavior. All I do is call y'all's names and holler and fuss. What do you get here? Positive infinity. The other side. Oh, I don't know. It doesn't matter which one you do first. I'm sorry. How about negative? That's right. This says the right side goes up, the left side goes down. All right. Now, I'm going to help you with the graphs of these. I want you to flip over to the back and X out the last three. We're not going to do those just yet. I'm going to give you the functions themselves. I can help you. You probably don't even. I'll graph the square root and the cube root for you just because we won't have graphed that yet. But the others, you should be able to graph on your own. Maybe cubic you won't be able to. We'll see. Let's go through and see what happens. Yes, we will get to those, but not yet. So reciprocal, exponential, and logarithmic, you can X those out right now. We will come back to them, but in future units, it'll be second half of the course. Huh? Yeah, you're gonna fill out the rest of it, but I'm gonna walk you through a couple. And yeah, this will be your homework. We were gonna do this and transformations, but just way too much for today, I think. Linear first. So this is have y'all heard of parent functions before? Huh? It is. It's what? Okay. So you haven't probably done a lot with it. Then have y'all talked about transformations? When you slide, shift, up, down, left, right, flip, stretch, shrink, all that good stuff. All right, so that's kind of what the goal of this unit is taking these parent functions and doing all this different stuff to them. So in order to show you how we do all that stuff, I need to go back and refresh some parent functions. So there's a definition at the top. They're a family of graphs display similar characteristics. A parent function is the simplest function of the family. You have a family of graphs. Does that make sense? It's just, you'll see. It's kind of like the quadratic. And whenever we started making it, we said it gets wider as A gets smaller and all that, and it shifts up and down. All right, so here's what we're going to do. I'm going to give you the parent functions. Some of them I'll graph for you or with you, and some of them you can graph on your own. So a linear function is just y equals x, or f of x equals x. And what does that look like when you graph it? Just the diagonal line. Y'all, everybody's doing their hands. But yes, this is just diagonal line 0, 0, 1, 1, 2, 2, and it just connects, and it's just, yours is going to be more accurate than mine. You make sure you put your points on yours so it's nice and accurate, because you'll use this as a reference later on the graph there. See the middle column? And I'm going to let you fill out the rest of that. You should be able to fill out all the other information there based on that linear. All right, moving on. And I'm just running through these kind of quickly. If you need me to slow down, let me know. But these we have done, and we've worked with a lot. The next is absolute value. That's the V. the equation itself, the parent graph looks this way. It's just the absolute value of x. Absolute value of x has a vertex where? At 0, 0, and its slope is 1, right? So up 1 over 1, and it b's right there at the origin. So that's the most basic absolute value graph that we have, and we will use that to do the transformations on from there. Quadratic, the parent graph, you would think it would be the ax squared plus bx plus c, right? But that already has stuff done to it. The parent graph is just x squared. It looks almost exactly like the absolute value, but it's not v. It's the parabola, right? So it doesn't come to a sharp point. It kind of eases down into it. So 0, 0, 1, 1, and then reflect into that. Same points, but different graph. If you went out another point, you'd see how it changes, because at 2, the absolute value graph would be 2, but at 2 here, you'd be 2, 4. So it should. Whereas the absolute value graph does this. I should make this a little smoother here. Cubic. Cubic is probably something new. In fact, the end behavior that I asked you to describe on that graph that y'all going, it looks like an S, it looks like an S. It was a cubic graph, actually. And the cubic graph is just x cubed. No, but it should be f of x, I'm sorry. Yeah, make sure it's f of x, just because they're functions. I get ahead of myself and get, yeah. Yes, we are. All right, points on a cubic. And let's just plug in a couple points. Think about a T-chart. 0, if I plug in 0, what do I get back out? 0. What if I plug in 1? 1, this is starting to resemble all the others. But what happens if I plug in -1? -1, because -1 to the third power, -1 times -1 times -1 is -1, right? So -1, -1. You are being a little weirdo. Stop. All right. So now I'm going to connect. Yes? So now this looks like what we did earlier. Two more that you haven't done before. You should be able to do all the analysis on here once I give you these little parent graphs. And I promise I'm almost done. This is actually a half of a parabola on its side. If you were to take the parabola and lay it over and take the bottom half off, that's what the square root graph would look like. Remember, what can I never put in a square root? A negative. So there's no negative x values on here. So I start with 0, 0. And what's the square root of 1? The next easiest point, just so that you can kind of see what the graph is looking like, would be to go out to the next perfect square, which would be 4. What's the square root of 4? 2. This just kind of so you can see, and now it goes like this forever. That's a square root graph. Is it continuous? Yep, it is. Bless you.
There's nothing on the bottom half.
Nope, there's nothing on the bottom half. The reason there's nothing on the bottom half is if I included that bottom part, it wouldn't be a function any longer because it wouldn't pack the back out. Last one. I'm going to give it to you just because you may need it for your project, but the next unit we get to, we will be a lot of radicals, and you'll see really where this comes into play. But the cube root graph, there's a little 3 that sits right here. You don't have to understand any of that just now. We will get to all that right now. I just want you to see what the graph itself looks like. Just like the squared was the parabola on its side, this is the cubic on its side. Okay, so when you do it, 0, 0, 1, 1, and -1, -1, it has the same starting points, but this time instead of going up, it's over on its side and it looks this way. Okay, it looks like the same thing, but it looks like it's been laid over. The cubic did this. All right, I'm not going to go into any more detail than that because you really, it's not